for now we'll continue this one. So we actually have seen the program memory organization. So just to recap, we have two types of memory, not two types of memory, we have two memories in PIC 18. What are those two memory? We have data memory and program memory. So we are just looking at program memory now. What is the capacity of program memory? 2 megabytes.
2 megabyte.
If you translate into plain bytes, you get 2,097,152 bytes, right?
Yes.
So what does it implicate? What does it actually show? How many locations that you can have? 2,097,152 locations. At every location, what is the maximum data that you can store? 8 bits or equivalent to 1 byte. Is it clear? So we have derived the range of address, right? We took the formula 2 by the power of n equals to 2,097,152 bytes, and therefore we get n equals to
21.
Why only the front telling the back what happened? Even though you're in the dark, I can still see you. I have night vision. What happened? 21 bits, right?
Yes.
So what we actually did in the previous class is we derived the range of the program memory address. So when n is actually equals to 21 in binary, so what we did, we actually wrote the long, did I write that? I didn't do that, right? And the last one will be all 111. And we don't actually always represent it in binary because binary address is too long. So what we do, we use the compact representation, which is the hex. So what we get, hex 000000, the maximum is hex 1 FF. Any questions on program memory? That means you always have 6 digits, 6 hex digits. So any question on program memory? Yes or no? So for now, that's all I want you to know about program memory. There are some other points here. All this we'll revisit back later on. Now take note that, did I mention about the reset vector? Thought I did. Whenever you power on, you always go back to reset vector. I did. Reset vector is actually the address 0. Remember I told you the address hex 000? That's the starting address of it. We have program memory. And you have your starting address which is 000. Of course it goes maximum to 1. Okay? So this one is known as the reset vector. Why is it known as the reset vector? Whenever you power up a system or you turn off and on back the power, the PC, what does the PC do?
Come back to start back.
What's the function of PC? PC. Very famous, right? I told you. What does PC do? Keeps tracks of the address of the next instruction to be executed, right?
Yes.
So automatically the PC comes back to this address. Are you all studying or not? Revising. Any question on this? So this address is known as reset vector. That means whenever you reset a system, the PC wherever it is, it will always come back to here. Any other questions? The rest of it we will cover later. So this is actually the diagram. Because this one we'll cover later. This is your PC. Your PC can access, because it has 21 bits, it can access these 2 million locations. Any point is 2 million location. So you see this first one is known as the reset vector. Of course you have the high priority interrupt, low priority interrupt. We'll revisit them back on chapter 6. So for now you can forget about it. And it goes up to maximum 1 FFFF as per what we have written here. This return address tag we will see in chapter 4. Okay, so for now I'm skipping that. So basically for now what you need to know is you need to understand what is the capacity of program memory. Based on the capacity of program memory, we have already derived the range of the address for the program memory. And you also know that each program memory location can only store 8 bits or 1 byte. And you have learned this term of reset vector, which is actually affiliated with this 0 address, which means whenever you reset a system, the PC, which is a project counter, always points back to this address 0. Is it difficult or easy? Now when you don't say something, that's a scary part. You don't know whether you understand, don't understand. Okay or not okay? So you are telling okay, so I'm moving on. So next is we're going to see data memory. Data memory has a capacity of 4096 bytes. It has a capacity of 4096 bytes. What does it mean? What does it mean? We have 4096 locations. And one here, how much you can store? Same, 1 byte. We have already covered this extensively. Now the same question applies here. If you have 4096 locations, how many bits do you need to address them uniquely in binary? You can take the same formula, 2 by the power of 10, 2 by the power of n equal to number of possibilities. So how many bits that you need? We have done this before, right? We did this for say what? For this program memory. Yes, you need 12 bits. Did everyone get this? Try to calculate and see. So the starting address will be the maximum one. So when you convert this, the same thing, the same concept only. This the limit is 2 million, so you get 21 bits. This is 4096, so you get 12 bits. You require 12 bits to address each one of them uniquely in binary system. So of course we would like to represent this in hex. So this one will become hex 000. This one becomes hex FFF. Is there any question? Okay or not okay? Okay or not okay? Okay. The same thing. So same thing with the data memory. What I want you to know is, I want you to know that the capacity is 4096 bytes, which means you have 4096 locations. And each location, to address them uniquely in binary, you need 12 bits. So therefore, you have this range of from 0 to 1, which if you represent it in hexa, you'll get hex 000 until maximum hex FFF. Is it okay? Now data memory is actually separated into two. They have special function registers. We have covered this before, right? I'm just covering again. Special function registers are used to control the operation of peripheral functions. We will see that later in detail. But what you need to know is data memory consists of GPR and also SFR. SFR means special function registers. GPR means general purpose registers. General purpose registers means you can just use them to store anything for a general purpose. You can use it for generally. But this special function register, you cannot simply load any values inside it because it will affect the characteristics of the CPU. So don't worry, we will see that later. So what you need to know now is, I think finals they asked this question. Last semester finals, they asked what is SFR and what is GPR. Easy question, right? Many did answer. Of course, if you notice that I'm skipping a lot of things in the notes, right? That's for a reason, because even explain now so you won't understand. So we will go past this, we will revisit some chapter, then we'll come back here, then you'll understand. So for now, how do we see this? This is your data memory. Do you see that from here to here is all GPR? Only the bottom one is SFR. So of course you can see the range of address is 000, maximum FFF. Of course, you say, what is this line, and all these things. We'll come back to that later. So all this GPR, this is SFR, special function register. So you cannot simply load any values here. It will change the behavior of the CPU. But this GPR, yes, you can load whatever you want. Is this okay up to this point? We shall move on. Access bank we'll skip for now because you won't understand it now. Now remember that we actually saw our CPU registers. This CPU registers is also known as special function registers. Remember the earlier diagram that I told that in CPU there is registers? That register is actually referring to this CPU register. Now what is the CPU register? Now the group of registers from FD8 to FFF is from here. Not from F60, is from somewhere in between here. So out of this SFRs, certain portion of it is used as the CPU registers. So they have a dedicated to general control micro control operation. So out of the currently, what are the two special function registers or CPU registers that will be introduced to you is the working registers and also the status register. Now we have seen the status register right before. What does the status register do? This is part of control unit, right? What does it do? It will actually it's like indicator, right? Whenever after you perform certain operation, addition, subtraction or things like that, it will actually indicate whether is there a carry, is there a borrow, is there an overflow. Okay, so that is status register. And then you see this working register, we will visit this working register maybe today or other time. So working register is involved in the execution of many instructions. If you see the instruction set, do you all have an instruction set? Can you just see the instruction set? Okay, this is the instruction set, right? If you notice in the instruction set, there's a lot of W. All this W are actually referring to the working register. So working register is nothing but like a normal register, but given a special name, working register. Why? Because it's easier to do this operation. When we do the example, then you can appreciate the working register. So for now, don't worry much about it. We will see that in a while. So these are the list of the CPU registers. For now, this is the address of the CPU registers or the special function registers, and these are the name. Because they are special, they are given name. They have a special name and they have description. So for now, we are seeing the status and also the working register. We will see working register in a while. We will focus on status. This is how a status register looks like. At address FD8, that means assume that this is your data memory. At address FD8, you have this location. This location is named as status. This is the address. But this address, this particular memory location is given the name status register. It is known as the status register. Now remember the term register. Register also refers to memory location. They are the same thing. They just have different names. So this is status register. Now in one location, remember there are 8 bits, right? So that's what it's showing here. That's the 8 bits. So you understand where this came from? Just like taking the whole slot out and displaying here. You understand? So one location can have 8 bits, but the status register is not using all the 8 bits. It's using only 5 out of 8 bits. So this bit is known as C, DC, Z, OV and N. What does it stand for? C means it is carry or borrow bit. DC means digit carry or borrow. Z means 0. OV means overflow and N means negative. So what happens is whenever you perform an operation, based on the result, this status register will give some output. Let's do for one example, a simple one, then later we'll actually revisit this one back. So let's say assuming you're performing addition operation, just for example, hack Don't worry about how we are going to do this. This one we haven't learned the instruction set yet. Later when we learn, then we'll learn how to do this addition part. For now, now we just want to focus on the status register. What I want to demonstrate now is when we perform certain addition with these two numbers, we get a result, right? How this result affects the status register. That is what I want to actually show. Is it okay? Now here something different. We are adding using a hex number. We are using a hex number. It is actually same as performing 2's complement or binary. Just that I am representing that binary number in form of hex. Can we solve this? 4 plus 9 is? You get? 13. What is 13? D. Decimal. 6. 7 plus 6.
D.
Okay, D.
No.
DD. This is the answer that you get, right? DD. Now, based on this answer, how will it actually affect the status register is you must ask yourself the question one by one. Now you have performed this addition. Later I'll tell you how you know that that particular instruction will affect the status register or not. Now take note that not all instruction affects the status register. How do you know? If you see your instruction set, do you see at the side that there is a column name labeled status affected? Some of the instruction it is mentioned as C, OB, DC, everything, right? What it means is that if you execute that instruction, all these bits in status register will be affected. There are some instruction which written there none, which means when you perform that instruction, it will not affect the status register at all. Now most likely those instructions are not arithmetic related instructions. We will see more example in that later on. So now we focus on this. Now we got to answer. Based on this answer, based on the result, always the result will affect the status register, and we are performing addition. Addition will definitely affect the status register. Now based on this, now what are the bits that we have? We have N, we have OV. Oops, I'm exceeding the limit. Can I erase this top part? So we have N, we have OV, we have Z, DC and so we have to ask ourselves one by one. First one is, this is C. C has two options actually. It's either carry or borrow bit. Carry happens when you perform addition. Borrow happens when you perform subtraction. This is digit carry and borrow bit. Digit carry means when you add these two, you get and carry out here, right? That is known as digit carry. After you add this, you have something extra than the 8 bits. That is known as carry. Is it okay? Now based on this result, do we have a carry? No, we don't have a carry. After you add this one, do you have anything? No, we don't have. So there is no carry. If there is no carry,
0.
this will be 0. This carry will be 0. Are you all following? Those at the back? You all want to be in brightness? Why today? I'll be in brightness one. Are you all following this?
Yes.
So the next question, do we have digit carry? Do we have digit carry? When we add this one, do we have a digit carry here? The next one, no, we don't have. So it will be 0. Is the answer 0?
No.
This one you have to be blind to make mistake. The answer is definitely not 0, right? So there is no 0. Do we have overflow?
No.
How you know?
There's no sign change. There's no sign change.
Is this number positive or negative? Is this number positive or negative? Answer positive or negative?
Positive.
Why? How you know this one positive?
Because I calculated
Huh? How you know positive?
change to binary.
D is what? 13, right?
13.
13 is what? 1?
1, 0, 1.
What is this?
Negative.
Negative, right? Overflow or no overflow? Overflow. Positive plus positive is supposed to get positive, you get negative. Take note that the value hex from 0, 0 until 7F are all positive. Is 0 until FF, they are all negative. Can anyone tell why? Why am I only writing 2 bits like this? 2 hex digit? Because we are always dealing with 8 bits. So I'm just writing this. Why am I categorizing the value hex 00 until hex 7F is positive, and why hex 80 until hex FF are negative? It's a very the white peanuts. See properly, you know the answer. Yeah?
The front bit of the binary will be 1.
Front bit of the?
The most MSG will be 1.
Yes. You see, this is the maximum, it goes until 7 here, right? That means from this until this range, the most significant bit always will be 0. From 80 onwards, the most significant bit always will be 1. So that's why it's negative. Is it okay? Supposed to be covered in digital logic actually. But never mind. So now when you see this, can you visualize the positiveness and negativity? So you know there's a overflow. So you don't need to convert everything, you just need to have the binary vision. So is the answer negative?
Yes.
Yes. So this is how the status register will know, will indicate what happens with the result. Is it okay? Okay or not okay?
Okay.
At the back, at the back, at the back.
So explain digit carry again.
Digit carry. Digit carry is when you add these 2 digit and you have a carry towards the next higher byte. This is actually the lower nibble. This is actually the higher nibble. 4 bits, right? 4 bits.
Yeah.
Whenever the lower nibble causes a carry over to the higher nibble, that is known as digit carry. Is it clear? So let's take another example of subtraction now. Can I erase this part? Okay, let's see this one. I just show the why I'm doing addition and subtraction. There's a reason why in a while. So now we want to perform subtraction. Do you still remember the rule? If you subtract same sign means it's possible or not possible to get overflow. If you subtract same sign. Don't think I'm asking you to test you because I also don't remember. I'm asking you.
Same sign not possible.
Okay. We have done confirmed. Sometimes I just teach but then I don't remember. I don't memorize it. So that's why I'm asking you. Okay, now we want to perform this subtraction. 2 minus 9? You cannot. So you need to borrow. How much are you borrowing? How much are you borrowing? 10. 2. 10. 16. This is basic 16 numbers. Hex number, so you are borrowing? 16. So 16 plus 2? 18. 18 minus 9?
No.
9. Correct lah. 6 minus 3? 3. You have X 39. Now let's see how does it affect the status register. Now since we are performing subtraction, instead of carry we look for borrow. Do we have borrow? No. There's a digit. This is known as digit borrow. Borrow means from this guy borrowing from this side. That is known as borrow. Do we have borrow?
No.
It's same like carry, have carry and digit carry, right? Same. We have borrow and also digit borrow. Borrow means the most significant bit is actually borrowing from the number before. That's known as the sign extension. Digit borrow means this guy borrowing from here. So my question is, do we have borrow?
No.
No, we don't have borrow. This guy never borrow from the other guy. Do you understand or not? There's two, borrow and digit borrow. Digit borrow is same like digit carry. Digit carry is the lower nibble adding, causing a carry to the higher nibble. Do you know that why each number is one nibble? Why? 4 bits makes up to 1 hex digit. Those at the back, can you all understand? And then there is also the higher nibble. When you add, you have a carry, right? That is known as carry. This one is known as digit carry. Likewise, if this number is smaller than this one, he'll perform a borrow. That is known as borrow. When this lower nibble doesn't have enough, it perform borrow. That is known as digit borrow. Can you understand? Yes. So now we have this. Again the question, do we have borrow? No. So what should be the value of C? 0. Take note here, there's something that you need to see. For borrow, the polarity is reversed. That means if got borrow means it will be 0. If don't have means it will be 1. It's reversed. Can you all follow? So now because we don't have borrow, so it should be 1. It is opposite to carry. Do we have digit borrow?
Yes.
So what should be the value here? 0. Yes, 0. Is the answer 0? No. Quite doubting, huh? Do we have overflow? Negative, same sign, both are positive, right? Subtracting same sign can get overflow or not?
No.
Impossible.
For subtracting same sign, impossible to get.
Possible lah. But I don't remember. So I'm asking
Yeah,
you.
it's impossible.
If I say impossible, impossible. Anyway, the answer is correct. A bigger positive number minus a smaller positive number, suppose you get positive and getting positive. Correct, what? 39 is positive, right? Okay? So we don't have overflow. Don't go and do reverse for all this thing, you know. Reverse only for DC and C. The rest are the same. You can see the phase reaction at UI. Only these two is reverse, huh? Rest followed and normal. Is the answer negative? Is the answer negative? No. So this is how it will affect status register. Now, what is the reason why they actually ask us to do reverse polarity here? The reason is, remember in one of our exercises in tutorial, what we did with the sign? What did I mention? Do we have a subtracting hardware? We only have adder, right? By right, it only performs addition. So what does it do with this one? So let's take the 39. 39 is actually 0, 0, 1, 1. 9 is 1, 0, 0, 1. We have to perform 2's complement of this, right? So you get 1, 1, 0, 0, 0, 1, 1, 0 plus 1. You get 1, 1, 0, 0, 0, 1, 1, 1. So what is this in hex? This is C7. C7, right? So the actual thing is, it will perform addition like this. When you perform addition, you get 9. This one, 17, 7, C is 12. 12 plus 7 is 19. 19 has exceeded the base number by 16, right? I mean, exceeded by 3. So you minus 16, you leave 3 and you have a carry, right? But the carry you don't bother now. This is the answer that you get when you perform the addition. When you perform the addition, N, O, B, C, I, C, C. Do you have carry? That is why. So that you'll get the same status. Do you have digit carry?
No.
Is it 0? No. Do you have overflow? Do you have overflow now?
No. 3.
Positive?
0.
If
No,
the
no.
unlike sign in addition, is it possible? Impossible.
Impossible.
Impossible. Is it negative? You see, you get the same answer. So that is why the polarity is reversed when you do subtraction, because in actuality is actually performing addition. In order for you to get the same status register, same status register status. Is it okay or okay? I'm not going to ask not okay because you're not going to say not okay anyway. Is that okay or okay? Any questions? At the back.
So that means
Only for
when it's followed by 0, that means we have. Is it?
Come again? Okay, if you perform, okay, just to summarize things up. Why actually I showed the, but yeah, the whiteboard looks a bit messy. Yeah. But if you're following the flow, you should understand. So the rule of the thumb is, whenever you're performing addition, you follow it strictly as it is. That means when the carry means, got carry, got digit borrow means 1. If don't have mean, it will be 0. Only for the carry and digit carry. The rest follow the same. Is it okay? Now when you're performing in subtraction, this sign here, when it's subtraction, these two you have to see in reverse. So if there is no borrow, by right it's supposed to be 0, but we make it 1. If there is no digit borrow, by right it's supposed to be 0, but you make it 1. That means it's reversed. Only for that. The rest, the Z, OB and N is the same. That is if you're performing subtraction. If like what I did now is, why I actually converted this to make it as addition, to show you why they are asking us to reverse. Because in reality it only performs addition. And this is how digital hardware performs addition. So when you perform addition, you get this value. By the way, when you subtract, you should get this same value. In order for you to get the same value, that's why they told to reverse these two. Okay? So remember, the thing is, if you see this negative sign, then you must reverse this. As long as you are positive, as long as you are performing addition, you follow the normal convention. Any other question? Any other question? Okay, for this subject, the best way for you to learn this subject is to participate in class. Well, that's one thing. The best thing that you can actually learn any subject is by teaching others. When you teach others, of course, sometimes it's too hard to teach. I also don't understand why to teach others. So, whatever you know, when you teach others, you will actually learn. So that's why you see, I actually learn a lot by teaching you all. So, and each time, every semester, I'm learning something, constantly learning. So it's also a learning process for me when I teach you this. But when you actually teach your friend, but make sure you teach the right thing, lah. Don't go teaching the wrong thing, die like you. So, but when you teach, you will actually learn more. And that when you teach your friend, you know, your friend can be your best friend, and the best friend also can be your worst nightmare. Because they'll ask a lot of questions. Why? Why like this? Why like that? If you can answer all your friends' whys, then sure, confirm here. So you just need to understand why we're doing certain things. So we have seen that we have actually demonstrated on how the status register is being affected with these two operations. I'm just showing these two operations. How to actually check. Definitely this one will be tested in your test 1. You see your past year test 1 paper. Any other questions regarding the status register? I think it's quite straightforward. We will do more exercises as we go along. Remember pipelining? We actually saw this when we actually studying the architecture of the PIC. We actually discussed why we actually have a separated memory, separated program and data memory. Now the separation of program and data memory is known as what architecture? What architecture is it known as? Yes, Howard architecture. If it's combined, von Neumann architecture. This question is very, very famously asked in test 1. A girl downloaded test 1 paper. When you plan to download? The day before test 1, that's where the thrill comes. The last minute thrill, suddenly ask a question, then your friend says, I don't know, I don't know. Then get panic, then together happily get panic. And come to the exam hall, not doing anything. Then in the exam hall, sir, give the question easy. What to give easy? Already print out ready. Just keep and do. So download, all the resources are already available. Download and check. When I'm telling you this certain thing, you can check and know, oh, like this. So why? So that whatever you're learning now, when you see the question, you can mentally prepare yourself. Oh yeah, this question I've asked before. Then immediately what you'll do, you'll take effort to memorize those. And you see, oh yeah, this question is all blah. All tests on same only. Suddenly you feel like that. So that's the reason why I'm asking you to see now. So don't wait until last minute thing. You know one thing, right? When you read a question and when you study something, automatically your brain will correlate with the question and also the answer. If you have ever done that before. Never mind. That is, I thought this one, they taught me in SPM, how to do this. We actually come across this term pipelining. We said that the separation of this program memory and data memory allows us to implement this pipelining. So what is this pipelining? I've already explained this pipelining, but here we have a diagram for us to actually illustrate. So you see, PIC can divide most of the instruction execution into 2 stages, like I mentioned before. There's instruction fetch and also instruction execution. So up to 2 instructions are done with execution. one instruction is in fetch while the second instruction is execution stage. Because of pipelining, each instruction appears to take one instruction cycle to complete. Now assume that you have a list of, assuming that you have written few lines of instruction. Now we're going to see how these instructions are being executed. So this TCYO means time clock cycle. Now time clock cycle is something like the base time for your digital hardware to work. Just for example, your watch. What is the base time of your watch? 1 second, right? Every second you can see that's the base time of your watch. What's the base time of your laptop? What's the base time of your laptop? Take the frequency and divide over. 1 over the frequency, you get the time. So you know how fast your processor works, right? So like that, you have every tick, like how your second is ticking. So every second, right? So like that, the first time when the first clock cycle, what happens? The control unit actually fetches this instruction, right? So the first time it fetch. Of course, there is no execution because now only we are starting. So it fetch. In the second tick, what it does, it executes the first one, at the same time it fetches. Now how is this possible? Because they are separated. That's why the execution and fetch can happen at the same time. The second clock cycle, this will be executed, the second one, and then it will fetch the third. So do you see this is known as pipelining? And I have also explained to you, if it's one-dimensional architecture, at every clock cycle we fetch, execute, fetch, execute, fetch, execute. So this is 2 times faster compared to one-dimensional architecture. So this is known as pipelining. So what is pipelining? Pipelining allows a simultaneous access of both memories by fetching the instruction and also executing. Same. This question also very popular question.